For years, scientists have had a hunch that black holes might reside at the heart of galaxies all across the cosmos. However, even though we can easily describe them using mathematics, black holes pose a puzzling challenge when it comes to imaging. How can we visualize something that engulfs everything, emitting no light in return, all while functioning in a parallel manner? Hidden behind clouds of cosmic debris and hindered by the interference of Earth's own atmosphere, black holes have been a challenging celestial enigma to observe. Yet, a recent milestone was achieved as a coalition of 300 scientists from 20 countries joined forces as part of the Event Horizon Telescope project to explore potential black hole targets within our cosmic neighborhood.
You see, our galaxy has this 4 million solar mass black hole, and we are on a collision course with the Andromeda galaxy. And I don't know how long, but many. And this black hole swallows everything else, dominates everything, doesn't swallow all the matter, probably most of it, though. And then it shrinks away because it loses its energy by Hawking evaporation.
You might remember seeing this picture back in 2019. It was the first big reveal from the Event Horizon Telescope, showing a massive black hole in the M87 galaxy. 2 years later, they shared an even more detailed image of M87, which showed a swirling magnetic field around the black hole. In colorful detail, this confirmed that the black hole compels matter to orbit around it at incredibly fast speeds. Scientists were observing the paths of gas circling the black hole. While the M87 images impressed people worldwide and demonstrated the Event Horizon Telescope's potential, the scientists were actually focused on a suspected black hole much closer to us, SAG-A, a star in the Sagittarius constellation. Hidden by clouds of dust and interference from our own atmosphere, black holes have traditionally been very difficult to see from Earth. But recently, 300 scientists working together across 20 countries as part of the Event Horizon Telescope project began to probe some prime suspects in our cosmic neighborhood. If you don't know, supermassive black holes have gained prominence as drivers of galactic evolution. But some observations of the Milky Way and its central black hole have not yet provided a coherent explanation. Last year, on May 12th, astrophysicists across the globe held 9 simultaneous press conferences to reveal the first-ever image of the black hole at the center of our Milky Way. Initially, this remarkable image of the glowing ring around the heart of our galaxy seemed to confirm what experts already anticipated. The Milky Way's supermassive black hole is real, it's rotating, and it follows Albert Einstein's general theory of relativity. But when we dig deeper, things don't quite fit together as expected. By studying the luminous ring of light, researchers have gauged the rate at which matter is being drawn into Sagittarius A, the name designed for our Milky Way's central black hole. Surprisingly, the answer is not very quickly at all. To explain, Priya Natarajan, a cosmologist at Yale University, likened the galaxy to a malfunctioning showerhead. It's essentially blocked to a mere trickle. Only a minuscule fraction, about 1,000th of the incoming matter from the surrounding intergalactic space, manages to reach and enter the black hole. This situation raises a big dilemma. Where does the remaining gas go? What exactly is transpiring with this flow? It becomes increasingly evident that our current understanding of black hole growth is questionable. In the last 25 years, astrophysicists have increasingly acknowledged the intricate and active connection between many galaxies and the black holes residing at their cores. Ramesh Narayan, a theoretical astrophysicist at Harvard University, remarks, "The surprise was that black holes are important as shapers and controllers of how galaxies evolve. These colossal voids, where matter is so densely concentrated that even light can't escape, function as the powerhouses of galaxies. However, researchers are just starting to discover the mysteries of their operation. Gravity plays a pivotal role by pulling dust and gas towards the galactic center, giving rise to a swirling accretion disk around the supermassive black hole. This disk heats up, transforming into a scorching white-hot plasma. Subsequently, when the black hole consumes this matter, whether in small increments or sudden bursts, it releases energy back into the galaxy, creating a feedback loop." Elliot Quaddart, a theoretical astrophysicist at Princeton University, says, "When a black hole grows, it generates and expels energy into its surroundings more efficiently than any other known natural process. This feedback process has far-reaching consequences, influencing the rates of star formation and the flow of gases throughout the galaxy. The mechanisms behind the active phases of supermassive black holes, when they become active galactic nuclei, or AGNs, remain shrouded in uncertainty. Key questions about what initiates these episodes and how they can be turned off remain elusive. Kristen Hall, from the Harvard-Smithsonian Center for Astrophysics, emphasizes, what is the triggering mechanism? What is the off switch? These are the fundamental questions that we're still striving to comprehend. In terms of size, our Milky Way, a typical spiral galaxy, occupies a middle ground. It was previously believed that our galaxy, with few visible signs of activity at its core, was primarily influenced by stellar feedback. However, recent observations indicate that active galactic nucleus, or AGN feedback, also plays a significant role. Researchers are delving into the intricate interaction between these feedback mechanisms within our home galaxy, and they're grappling with enigmas like the current dimness of Sagittarius A. By studying this interplay, astrophysicists wanted to gain insights into the coevolution of galaxies and black holes in a broader context. The Milky Way is evolving into a potent astrophysical laboratory, providing a microcosm that may hold the key to understanding these complex processes. By the late 1990s, astronomers had widely accepted the existence of black holes in the centers of galaxies. They could now measure the mass of these invisible objects by studying the movements of stars around them. What emerged was a surprising correlation. The larger a galaxy, the more massive its central black hole. This connection was remarkably strong and groundbreaking, indicating a communication between the black hole and the galaxy, as described by Tiziana De Matteo, an astrophysicist at Carnegie Mellon University. This correlation is intriguing when you consider that the black hole, despite its significant size, represents only a small fraction of the galaxy's overall mass. For instance, Sagittarius A weighs approximately 4 million times the mass of the Sun, while the Milky Way totals around 1.5 trillion solar masses. As a result, the black hole's gravitational influence is primarily concentrated on the innermost region of the galaxy. To Martin Rees, the United Kingdom's Astronomer Royal, active galactic nucleus feedback provided a natural link between these relatively small black holes and the larger galaxies they inhabit. In the 1970s, Rees had correctly proposed that supermassive black holes generate the luminous jets observed in distant, brilliantly shining galaxies known as quasars. He also suggested, along with Donald Lyndon Bell, that a black hole might explain the glow at the center of the Milky Way. This raised the question, could this be a universal phenomenon governing the sizes of supermassive black holes everywhere? The concept was that the more matter a black hole consumes, the brighter it becomes, and the increased energy and momentum push gas outward. Eventually, this outward force counteracts the gravitational pull on gas, preventing it from falling into the black hole. That will terminate the growth. In a simplified way, that was the logic, Rees explained. In De Matteo's words, the black hole eats and then swallows. A larger galaxy places more pressure on a central black hole, making it more challenging to expel gas, allowing the black hole to grow before eventually consuming it. Nonetheless, very few astrophysicists were initially convinced that the energy generated by infalling matter could be expelled in such a dramatic fashion. As Priya Natarajan, who contributed to the development of the first active galactic nucleus feedback models during her time as a graduate student under Rees, recalls, "When I was working on my thesis, we were all focused on black holes as points of no return, just gas going in. Everyone had to approach it very cautiously, as it was considered so radical." Confirmation of the feedback concept arrived a few years later through computer simulations devised by Tiziana Di Matteo, along with astrophysicist Volker Sprinkel and Lars Hernquist. "We aim to recreate the incredible diversity of galaxies we observe in the real universe," Di Matteo explained. They were aware of the fundamental progression. Galaxies start small and dense in the early universe, and over time, gravitational forces lead to the collision of these dwarf galaxies, forming a variety of shapes, from rings and whirlpools to cigars and more. Eventually, galaxies grow larger and more diverse, until after numerous mergers, they become large and smooth, resembling a blob, as Di Matteo described it. However, there was another problem. While spiral galaxies like the Milky Way have many young blue glowing stars, giant elliptical galaxies consist mainly of very old red glowing stars. Springle noted, they are red and devoid of new stars. Yet in each simulation, elliptical galaxies were emerging with a blue glow. Their computer model failed to capture whatever was halting star formation. Then Springle explained, we had the idea to introduce supermassive black holes in the center of our galaxy mergers. We allowed these black holes to ingest gas and release energy until the entire system was expelled, much like a pressure cooker. Suddenly, the elliptical galaxy would cease star formation and transition to being red and star dead. Springle was stunned by the results, stating, my jaw dropped. We did not expect the effect to be so extreme. By producing red and dead elliptical galaxies, the simulation lent support to the black hole feedback theories proposed by Rees and Natarajan. It demonstrated that despite their relatively small size, black holes can communicate with the entire galaxy through feedback. Over the past 2 decades, these computer models have been refined and expanded to replicate substantial portions of the universe, closely mirroring the diverse array of galaxies observed in our cosmos. Additionally, these simulations reveal that the energy ejected by black holes fills the space between galaxies with hot gas, which would otherwise have cooled and formed stars. Volker Springle notes that people are now convinced that supermassive black holes are very plausible engines. No one has come up with a successful model without black holes. Despite the advancements in computer simulations, there are still big uncertainties in our understanding of active galactic nucleus feedback. As matter slowly spirals inward toward the accretion disk around a black hole, friction leads to the release of energy, and this energy loss is something that simulation developers incorporate in their models through trial and error. This trial and error approach indicates that some of the finer details remain elusive. As Elliot Quattart puts it, there's a possibility that in some cases we might be arriving at the correct answer for the wrong reasons. Maybe we're not capturing what truly matters in how black holes grow and distribute energy to their surroundings. The fact is that astrophysicists have not fully comprehended how AGN feedback operates. Astrophysicists know it's crucial, but they are not entirely sure about the exact mechanisms behind this feedback. The primary challenge is that they lack a deep physical understanding of feedback. What they do know is that some of the energy is emitted as radiation, which contributes to the characteristic brightness of active galaxy centers. Strong magnetic fields also leads to the ejection of matter from the accretion disk, forming either diffuse galactic winds or powerful focused jets. The Blanford-Znajek process, identified in the 1970s, explains how black holes generate jets, but determining the jet's power and how much of its energy is absorbed by the galaxy remains an open, unsolved problem. The galactic wind, which spreads out spherically from the accretion disk and has a more direct interaction with the galaxy compared to the narrow jets, is even more enigmatic. The billion-dollar question is, how does the energy couple with the gas? One indication that there's still room for improvement is that the black holes in cutting-edge cosmological simulations often end up smaller than the actual observed sizes of supermassive black holes in certain systems. In these simulations, in order to halt star formation and generate red and dead galaxies, black holes must expel such a substantial amount of energy that it obstructs the inflow of matter, causing the black holes to cease growing prematurely. Priya Natarajan describes it as the feedback in the simulations being too forceful. It hinders growth prematurely. On the contrary, the Milky Way presents a different challenge. Simulations usually project that a galaxy of its size should have a black hole between 3 and 10 times larger than Sagittarius A. To gain a deeper understanding of how AGN feedback truly operates, researchers are focusing on an in-depth study of the Milky Way and neighboring galaxies. This will hopefully allow them to understand the intricacies of this phenomenon. In December 2020, scientists using the eROSITA X-ray telescope found 2 enormous bubbles above and below the Milky Way, similar to gamma-ray bubbles discovered by the Fermi telescope a decade earlier. The origin of these bubbles had puzzled scientists. Some thought they might be from a jet shooting out of Sagittarius A millions of years ago, while others believed that they were due to the energy from exploding stars near the galactic center. When Shang-Yi Karen Yang saw the X-ray bubbles, she realized they might share the same source as the gamma rays if they came from the same AGN jet. Along with colleagues, they created a computer model that not only matched the bubble shapes, but also suggested they formed quickly, within 2.6 million years, too fast for stellar feedback. This finding showed that AGN feedback could be more important in galaxies like the Milky Way than previously thought. It's like an ecosystem where AGN and stellar feedback interact with the hot gas around galaxies. The Milky Way's history could reveal more about these processes. The Gaia telescope, for example, shows that the Milky Way likely didn't undergo a merger when the Fermi and E Rosita bubbles formed, challenging the idea that mergers trigger AGN jets. On the other hand, the interaction between blobs of gas and the black hole might be more random, where they collide and sporadically activate it. This process could involve the black hole alternating consuming matter, expelling energy through jets and galactic winds, and taking breaks in between. The image we showed you of Sagittarius A, captured by the Event Horizon Telescope, which depicts its current slow intake of matter, presents a fresh puzzle. Astrophysicists were already aware that not all the gas drawn into a galaxy would reach the black hole's event horizon, as galactic winds push outward against this inflow of matter. However, the strength of the winds required to explain such an extremely tapered flow appears unrealistic. As Ramesh Narayan explains, when I run simulations, I don't observe a substantial wind. It's not the type of wind that would provide a comprehensive explanation for what's happening. Understanding the inner workings of galaxies presents a hard challenge due to the vast differences in scales between stars, black holes, and entire galaxies and their surroundings. When conducting computer simulations of physical processes, researchers must choose a scale and include the relevant effects at that scale. However, in the context of galaxies, both small and large-scale effects interact, creating a complex web of interactions. The black hole is truly tiny compared to the large galaxy, and you cannot incorporate them all into a single massive simulation. Each scale requires information from the other, but they don't naturally connect. To bridge this gap, Narayan, Priya Natarajan, and their colleagues are launching a project that employs nested simulations to construct a coherent model of how gas flows through the Milky Way and the nearby active galaxy Messier 87. In this approach, information flows bidirectionally, with the galaxy informing the black hole's behavior and the black hole, in turn, influencing the galaxy's dynamics. As Narayan describes it, it's a loop that goes round and round and round. These simulations should shed light on the flow patterns of diffuse gas within and around galaxies. Observations of the circumgalactic medium by the James Webb Space Telescope will also contribute to the understanding of this dynamic. As Elliot Quattart says, the gas's journey down to the black hole is a crucial aspect of this entire ecosystem, as it fuels the energy expelled by the black hole. In this new approach, all inputs and outputs between simulations of varying scales must be internally consistent, reducing the number of adjustable parameters. As Narayan explains, if the simulation is properly set up, it will self-consistently determine how much gas should reach the black hole. We can investigate and ask why it didn't consume all the available gas or why it was selective in taking in so little of the available gas. The team aims to create a series of snapshots of galaxies during different phases of their evolution. At present, much about these galactic ecosystems remains speculative. As Xiangyi Karen Yang points out, it's a new era where researchers are beginning to explore these interwoven scenarios. While definitive answers may be lacking, the hope is that in a few years, a clearer understanding will come to all of us who gaze at the sky with wonder. Until next time, maintain your curiosity. The space is vast, and the questions will only get bigger.